There we go. Okay, so how's everyone feeling? I see some nodding, I see some shaking, I hear some silence. We have a midterm tomorrow, and yeah, it's I'm getting lots of emails. We've, I think, been trying to provide a lot of support in the form of office hours and tutorials and video recordings of different things. I think that's all great practice. And I kind of feel like when we make exams and midterms, I kind of run out of ideas. So from that perspective, you know, old exams and midterms are a great source of practice questions. Those assignments, the practice assignments, I've been looking at those as well. Those are good, but they're also old. Like we made those before we had sapling. So the emphasis, I would say, has shifted a little bit in the course since then. And one thing I definitely noticed was we shifted, I would say, quite a bit away from testing a lot on nomenclature. So if you went to class and we didn't really talk much about it, I posted a tutorial on how to do alkane nomenclature, and then you get to this assignment and it's like 50% nomenclature with all these weird little, we're not going to be going too hardcore into that element of this stuff. I think more and more that nomenclature stuff people are covering as early as high school. And to me, it's also not very interesting. It's like you memorize a bunch of rules and then you can name a compound, which you could have drawn the same compound into computer software and it would produce that name for you. So learning all the little nitty-gritty rules, I'm less worried about. Although if I do say something like, 2-methyl, that's a name I would expect you to be able to draw. Fair enough. In terms of today's class, I spoke with Terry about what we wanted to do today, and we kind of decided that we will continue with chapter 6. And the reason is we have basically all day today is office hours, on and off. So for me, I think I'm going from right after this class until 11, and then Terry picks up at 11. And I think she has maybe half an hour plus an hour at the end of the day, once labs are done. Plus, she had 2 sessions on the weekend, plus all the videos that were made and posted. So please, if you have any particular questions or any sort of burning issues for this midterm, please just let me know or her know during office hours. Get in touch and we can address it then. Fair enough. Cool. So what we have covered last class, we started Unit 6, and Unit 6 is when things start to get interesting, start to get exciting. You may disagree, or maybe you like something else we've done already better, but we covered our first reaction, right? In fact, I wouldn't say first reaction, I would say first mechanism. Does anyone remember what the mechanism was called? Started with S. And 2. Does anyone remember what any of these 3 symbols means? This one was substitution. And what does substitution mean? You remove, added something different, right? So we've substituted some part of the molecule for something new. How about N? Yes. Nucleophilic. And what about the 2? 2's telling you something about the mechanism. In particular, telling you something about the rate determining step. Bimolecular. Thank you, Sophie. And we drew a mechanism that looked kind of like this. Let's say you have something like carbon, hydrogen, 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 iodine. I'm going to draw in all our lone pairs. Okay, and we're going to add something to this that is what we call a nucleophile. Nucleophiles are things that love positive charge. Nucleophiles are often negatively charged. Negative charges love positive charges, and it must have a lone pair of electrons. So I'm going to choose something like this. What's that thing that I drew? C triple bond N with a negative charge. Ever seen it before? It's called cyanide, right? Cyanide anion. Cn minus. That's its Lewis structure. Negative charge on the carbon, negative formal charge. So that thing would love getting somebody's mic here. That loves the positively charged carbon. And that will knock off the iodine. And what you'll get is carbon, hydrogen, 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 and all right. So in this case, you can see we've substituted the iodide for cyanide. Now, this mechanism is everything I drew here. The mechanism is a single step, and that step is bimolecular. That bimolecular step just means there are two things that collide in the rate determining step, which is the only step in this particular reaction. So the cyanide is the first thing, which we call the nucleophile. And then we have the rest of the molecule, which we often call the substrate. And the carbon is attacked from the backside by the nucleophile and knocks out the iodide. And remember we talked about the cars parking and how if you wanted to knock the car out of the spot, you could drive and ram and hit the car from behind. That's exactly what's going on in this particular mechanism. One other thing that we talked about happens to that carbon is the carbon itself undergoes what we call inversion. Right? We talked about it's like when you have an umbrella, the wind catches it and inverts the shape. The same thing happens with the carbon, such that if you have an example that looks like this, let's instead use a molecule like this, where we have a chiral center, and we have the same nucleophile. This can do an SN2 to do something like this. So where that group that was there before, the iodide, is coming towards us, the group that replaced it, the cyanide, is going backwards. So it converts an alkyl halide, in this case, to a nitrile. Right? Because there's a carbon triple bond N in the product. And you can do this. You can buy cyanide, sodium cyanide, and you can react alkyl halides with sodium cyanide and turn them into nitriles. So this is the first example of a reaction where we're converting one molecule into another molecule. And this, might seem boring and not a big deal to you guys, but about 200 years ago, yeah, maybe 300 years ago, 250, this would have been a huge deal because people believed that the only way you could get organic molecules was for a living system to produce them. And that living systems had some sort of magical, what they called a vital force. And without that magical vital force, organic molecules couldn't be made. And we've since realized that if you know what's going on, you can make basically any organic molecule you want, starting from inorganic starting materials. The first person to do this was a guy named Frederick Wohler, and he took an inorganic compound called, what was it? Something isocyanate, and he ammonium isocyanate, and he heated it up and he turned it into urea, which is an organic molecule found in urine, among other things. So we're doing this again. We're taking molecules. I mean, I guess we're starting out with something organic, but we're converting it into something new. And that's really the whole point of organic chemistry, right? We spend a lot of time talking about structures and understanding shapes, and that's necessary for what's coming. But the science of organic chemistry is not about understanding how things are shaped or how they rotate or all this sort of stuff. It's really about how can we convert what we have into something new. So this is how we're going to do it. First of all, with SN2 reactions. So this SN2 reaction, we have a name for this kind of reaction where this, every single time the reaction happens, it will invert the stereochemistry of the carbon where the leaving group is. So we call a reaction like this stereospecific. Stereospecific means you get the same stereochemical outcome every single time. So if you have this molecule, which is the R2-bromooctane, it will replace the bromine with the hydroxide in this case, such that if it was going back before, it'll be going in front. So it's inverted it. Alternatively, if you started with the enantiomer of that starting molecule and you do the same reaction, the product you get will be the enantiomer of the product that you get from the other one. And this is actually the technical definition of a stereospecific reaction. It's that a single stereoisomer of your starting material will give a single stereoisomer as a product, whereas a different stereoisomer of the starting material will give a different stereoisomer of the product, but only that product as well, which is a little bit confusing to think about. But basically, what I want you guys to know is that when you do this SN2 reaction, every single time that stereocenter gets inverted. That's a feature of SN2. And it's something you got to watch out for, because if you spend months in the lab as a medicinal chemist working for Pfizer and you're trying to make some particular compound to fit into some receptor, and you built in chirality, so you have a chiral molecule, you're all set, and then your last step is an SN2, and then all of a sudden in your last step you invert your stereochemistry, and now you have the wrong isomer. You don't want to fall into that trap. All right. In terms of rates, the SN2 rates depend a lot on the structure of your starting molecule. So all of the examples we've seen so far with SN2 are reactions with alkyl halides, where a leaving group, remember the leaving group, the part that leaves, is a halogen, like iodide, chloride, bromide. If you use ethyl, you know, the carbon is the carbon on an ethyl with the X being bromine or something like that. We're going to use this as our sort of standard. And we're going to say that it has a relative rate of 1. So everything else we're going to be comparing to this. If you take that methyl off and just look at methyl bromide instead of ethyl bromide, what happens is the reaction becomes 30 times faster. It accelerates by a factor of 30 by taking that methyl group off there. And if you think about what's going on here, right, we have this carbon, this nucleophile with the lone pair of electrons has to kind of squeeze in and donate those electrons to the backside of that carbon. And this methyl group, you can see it's sort of drawn as a big kind of oval. It's kind of protecting the backside of that carbon. So it's a little bit harder, you know, the nucleophile's got to come in at a bit of a different, you know, approach. Got to come in from behind, but, you know, any nucleophiles that are up here can't really go anywhere because they're blocked by that methyl group. So if you get rid of that methyl group and you have all little tiny hydrogens, the reaction rate gets a lot faster because the nucleophile has an easier time getting itself to the carbon. So it makes sense if you go to a secondary alkyl halide. Secondary alkyl halide would be something like this. The secondary alkyl halide has 2 carbons, 1, 2, attached to the carbon with the leaving group. And it's even harder for the nucleophile to get in because it's got 2 methyl groups that are blocking the backside of that carbon, which the nucleophile has to get past to do this reaction. Doesn't mean it can't get in there, but it just means it has to be either moving very fast or comes in at just the perfect angle. You can see the reaction becomes about 30 times slower yet again. Okay. If you put a giant group, now every time in this course you see tertiary butyl. Tertiary butyl group is drawn like this. So if you put a molecule like that, that group is so big and takes up so much volume and likes to spread out that it makes it near impossible for the nucleophile to get its way into this carbon. See, it has to kind of squeeze in here and get in there somehow. That T-butyl group does an exceptionally good job of blocking that side of the molecule. So you see the rate here is like super small. It's like what? That's 100,000 times slower than if you just had a methyl group there, like in this case. Finally, if you have a tertiary alkyl halide, like this, that's a tertiary alkyl halide. Its reaction rate is 0. It doesn't react at all. And the reason is the 3 methyl groups essentially close up all of the space on the backside of that carbon. That nucleophile really has no way of getting in there, and so the reaction won't work. So SN2s work best when you have a really unrestricted carbon. There's nothing groups as those where those 3 hydrogens are to block things. If you add 1, you make it slower by a factor of 30. Add 2, make it slower by a factor of like 300. Add 3, and basically it's game over. Okay. So tertiary alkyl halides, we say, don't react by SN2. Okay, and this is kind of like if you go back to our car analogy, right? Let's say there's a parking space here, and there's a car in that space, right? And you are trying to come in. You are the nucleophile in this story. You want to come in and you want to knock that car out. So this picture I have here is like as if you had, you know, let's say you have a little bush here, a little bush there, you know, just small little features kind of off to the side. This would be like if you have a carbon with little itty-bitty hydrogens. No problem. Nucleophile can come in and knock it out. When you put something bigger on there, it's as if you took like a, I don't know, like let's say you took, what's something big? Let's say there's a garbage can there. That's not very big. A garbage can filled with concrete. There we go. There's a garbage can filled with concrete there. You can still hit that car out, right? But you got to be a little more careful, right? You don't want to hit that. When you go to something that's tertiary, CH3, CH3, it's almost as if you put like 3 things full of concrete there, and now you can't hit that car anymore. It's blocked, right? So just the same way, a tertiary alkyl halide has the backside of that carbon blocked, so you can't have an SN2. Well, that's too bad, right? That means SN2 is a little bit limited in what you can do with it because it doesn't work in every possible alkyl halide. But it works out if you took something like this, which is a tertiary alkyl halide, put it in with a nucleophile. In this case, we're going to use a solvent, acetone, and water. And you're going to heat this up. The substitution still takes place. The hydroxide goes on, the chloride leaves, So substitution still happens. In fact, the substitution will happen faster than it would if it's primary or secondary. So what's going on here? I said SN2 doesn't work if it's tertiary, but I'm telling you substitution is still taking place. How do those two statements make sense with each other? Sam, yes, I see your hand up.
Oh, I had a question a while ago. I don't know the answer to this.
Okay. Do you still want to ask the question?
No, it's fine. I'll ask it later.
Okay, sounds good. All right. So the only way that you can have a substitution take place if SN2 is impossible is to do it some other different way. We're going to do substitution, but we can't use the SN2 mechanism. So if you do this thing with the initial rates method, remember you kind of vary the rates of the nucleophile, you vary the rates of the substrate in different experiments, and you compare the overall initial rates, you can end up determining the rate law for the reaction. So we did that before for SN2 and we found it was bimolecular. That's where we got the 2 from in the name. And we said if you doubled the concentration of the nucleophile, you double the reaction rate. If you double the concentration of the substrate, you double the reaction rate. Well, it turns out for tertiary alkyl halides, when you undergo substitution here, you do that same thing, the rate law just is this. The rate law is K times the concentration of the substrate. The nucleophile doesn't appear. So this means it's not SN2. This is not bimolecular. This is unimolecular. The rate determining step here only involves one molecule. So we're going to have a reaction where the nucleophile doesn't even factor in to the rate determining step. So it's not SN2, but we know it's unimolecular. In other words, the order of the reaction is equal to 1. So what do you think we're going to call this one? The other one was bimolecular and we called it SN2. This one is unimolecular. We're going to call this one SN1. So we have a different mechanism which takes place if it's tertiary, which is great. And there's a lot of info on that slide. I want to come back here. Remember we said before, when you want that parking space, 2 ways to go about taking that spot. One was to ram it out, which we said before was SN2. The other one is to wait for that car to leave all on its own. So basically there's 2 steps. The first step is wait until car leaves. Second step is drive into empty space. Which of those is the slow step, do you think? Yeah, the first one, you may have to wait a long time for that car to decide to drive away and leave that empty space. But once it does, it takes no time to drive into that empty spot. So this is kind of like a 2-step mechanism where we have a slow step, we have a fast step. Okay, so we're going to wait for the leaving group just to leave all on its own, and we're going to drive in and occupy that space. All right. So here's an example. We have step 1. We have our tertiary alkyl halide, which can't do SN2 because the backside is too blocked up. And what happens is this carbon-chlorine bond just breaks. Why does it break? We're going way uphill in energy to break that bond. The reason is because we are at room temperature, or warmer maybe. And we have energy in the system. We have things banging into each other, colliding, going this way, going that way. So this just might be the result of an unlucky collision, which gives this molecule enough energy to get over that hump and break that bond. So what happens is that carbon-chlorine bond, you can imagine it kind of stretching first. Imagine it being like an elastic. Taking an elastic band and you stretch it, stretch it, stretch it. The strain gets higher and higher. And then eventually you pull it hard enough that it snaps and then they're apart. It's kind of like what it's like to break a bond like this. That as you start stretching it, the tension goes higher, 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 higher until you hit the transition state, and it snaps. And then now, once it snaps, you have your separate ions. You have your chloride ion, you have your carbocation, and both of them are there. This is a single step. Where's the nucleophile? There's no nucleophile here, is there? Right? Think of this as being like the parking lot with an empty space. Why is it an empty space? Because that's a carbon with a plus charge. That's 6 valence electrons. It's a parking space for another electron pair. So something with an electron pair can come in and dock, react with this carbon. The nucleophile is like you waiting for that empty space to open up. That nucleophile is just kind of hanging out. It's not involved in this step. All it can do is sit by and watch. The only thing that happens in this step involves just one molecule. This is a unimolecular step. Okay. So we make this carbocation intermediate. We talked about carbocations a little bit before. Carbocations are carbons with a positive charge with less than a full octet of electrons. They're not very stable, but maybe there's ways to stabilize them a bit. It turns out that alkyl groups are electron releasing or electron donating. We'd mentioned this before for alkyl groups back when we looked at acid-base properties, and we said there's electron withdrawing groups, which are electronegative. There's electron donating groups, which are typically alkyl groups. This positive charge is unhappy because it has a carbon, positive charge, not a full octet. It's electron deficient. So by having alkyl groups like methyls or ethyls or things like that, what those can do is donate electron density into where that positive charge is. And by donating those electrons or electron density into there, that helps stabilize that. If you think about carbocations, you can have a methyl, a primary, secondary, or tertiary. Now we're talking about tertiary now because tertiary alkyl halides can't do SN2, they have to do SN1. What we see is in this example where we have all these different carbocations, the most stable one of these is going to be tertiary by a long shot. And the reason it's most stable, it has 3 alkyl groups all releasing electron density into that positive charge that helps stabilize that positive charge. Okay, they push electron density in through what we call the inductive effect, which we had talked about a little bit earlier. Great. So we make these carbocations. These carbocations are typically high in energy. Even if they're tertiary, they're high in energy. But yeah, we can make them a little bit better by having alkyl groups attached. The more, the better. So this is the scale. Most stable is tertiary. The least stable is methyl. And in fact, these two are so unstable, they never form. And when I say they never form, maybe they form in the clouds of Titan or something like that, but like in solution in this course, you'll never be drawing a methyl or a primary carbocation. They don't form under ordinary chemical conditions that we're going to create. Okay. Now, that's okay because if you have a methyl or primary alkyl halide, they can just do SN2, no problem, right? It's the ones that are tertiary and maybe some of the secondary ones that'll have a hard time doing SN2, so they can do SN1, which is good because they can make reasonably good carbocations. All right, this is another picture showing the same thing. So this is just showing the barriers, the energy barriers associated with this step one, with this breaking that carbon-chlorine bond. The height of that barrier will depend on whether the carbocation is primary, secondary, or tertiary. Tertiary, as you see in this example, is pretty stable, relatively speaking. It's still definitely uphill. It's still definitely the case that the carbocation is less stable than the starting material. Still going to be a slow step, but you know, the difference between here and here isn't that bad. But like the difference between here, way up, and here, this is really high. So what we find then is trying to make a primary or a methyl, the barrier is simply too high. The energetics just don't work out. We can't get a solution hot enough to make these reactions proceed at any reasonable rate. You can keep adding heat, but what happens is then you start breaking other bonds and your solvent catches on fire and all these other things start to happen. So yeah, we can't really do it with those two, but you can definitely do it with a secondary and a tertiary. If you compare these two reactions, so this is an alkyl halide reacting in this case with sodium bromide. So here's a general rule I'm going to tell you that you're going to use many times in this course. Anytime in this course you see sodium anything, or lithium anything, or potassium anything, any kind of group 1 metal attached to something else, immediately in your mind, split them apart. So NaBr is not sodium bromide, NaBr is Na+, and then way over here, Br-. And do that with anything you see. If you see potassium or sodium, get rid of it, pull it off, make it a cation, and then whatever's left will have a negative charge. Okay, so we have in this case our alkyl halide. We're going to react it with sodium bromide. In reality, bromide is going to be the reacting species here. That's going to be our nucleophile. It's a good nucleophile because it's got a negative charge on lone pairs. And it wants to come in here. Now, in both of these examples, we have a secondary and tertiary alkyl halides. They're a little bit difficult for a nucleophile to get past because, you know, the backside of that carbon is kind of blocked. So what happens instead is these reactions can happen by SN1. Basically, the chloride leaves to make a cation, this or this. Then the bromide is like, sees the empty parking space and jumps in. It turns out the reaction is significantly faster with the tertiary alkyl halide. Because it's easier to make the carbocation, that step one happens faster, because tertiary carbocations are pretty slow. And this is what this means in practical terms. If you went to the lab and wanted to do this reaction, maybe at room temperature, in 2 hours, this reaction would be complete. Whereas maybe to get the secondary one to go, you might have to heat it up to the boiling point of water and even wait overnight, wait like 12 hours. So, you know, these rates that I'm talking about have a very practical importance if you are trying to do these in an actual lab or in a, you know, in a factory or something like this where you're trying to do these chemical steps. Yeah, to get comparable yields there, it requires less time and less harsh conditions. So if you can make a reaction happen quickly, that's generally what you want to see take place. So primary alkyl halides can't do this. They can't do an SN1 because primary alkyl halides cannot make carbocations because primary carbocations are no good. Primary alkyl halides, though, they can do SN2, right? They're best for SN2 because they're not blocked. So this is actually pretty good. If you think about these two mechanisms, SN1, SN2, alkyl halides are going to pick one of these two mechanisms to do a substitution. If it's primary or methyl, it can only do SN2. It can't do SN1 because you can't make the carbocations, they're too unstable. If it's tertiary, it can't do SN2 because the backside is blocked up. So if it's tertiary, all you can do is SN1. The odd one out is a secondary. Secondary alkyl halide. They can do either SN1 or SN2, depending on the situation. The rule is easy for the others. Primary methyl, do SN2. Tertiary always does SN1. Secondaries, we got to look a little closer. It depends. It can do one or it can do the other. And don't worry, we have guidelines to predict which is going to be major. In terms of stereochemistry for SN1, here's an example where we have a chiral tertiary alkyl halide. So the rate determining step is making this carbocation. We lose the leaving group, and we have a nucleophile here, which is going to be water. Water is actually a pretty good nucleophile. It's got lots of lone pairs. You can have lots of water in solution. And you make this carbocation, and then the water can come in. What happens is we start out with something that's what we call stereochemically pure. Something that's chiral, something that only has our stereochemistry. We might say it has a high enantiomeric excess or a high optical purity. If you've seen that stuff yet from chapter 5. But when we do this reaction, we lose the chloride, we make a carbocation, and that carbocation is planar. It's flat, right? That carbon has 3 electron groups. It's trigonal planar. So trigonal planar means that it doesn't have any chirality anymore. Once the leaving group's gone, no chirality. The nucleophile, in this case the OH2, the water, it can attack the front or the back. Think about this molecule as like a flat plate now, or a flat, I don't know, something that's flat. What's something that's flat? A cutting board. I don't know why that came into my head as the first flat thing I could think of. That water can attack the front or the back. It doesn't make any difference. It's the same. The both faces are exactly the same as each other. There's no preference for the OH to come into the front or to the back. So if it comes in the front, you get this one. If it comes in the back, you get this one. And you'd expect to get exactly 50-50. Because the energy of those two products is the same, because they're enantiomers. No difference. And if each of them lose H+, you can make an alcohol that's R or an alcohol that's S. You get a racemic mixture. You get exactly 50-50. And that kind of sucks. If you think about it, you started out with something that was stereochemically pure, which is generally something you want if you're making, say, a drug, a pharmaceutical, for example. You want only one. You only want the one that works, or the one that has the activity in the body that you are looking for in the molecule. But if you do an SN1, because you make a carbocation that's flat and planar, you lose your stereochemistry. We say this proceeds with a loss of stereochemistry. SN2 inverts it, right? Inversion we can kind of handle, but loss, now you got a racemic mixture, and these things are very difficult to separate from each other because they have all the same chemical properties. You can't distill them because they have the same boiling point. Can't typically recrystallize them. There's all these methods you might use to purify chemicals that don't really work here. So that's a feature that's very different between SN1 and SN2, and a very important one if you're trying to use these reactions to convert one molecule to another. Same way, I guess, in the car in the parking lot. If the car leaves, you can drive in from the front of the or the back. Doesn't matter. The two, anyway. Maybe I'm stretching that too far. All right. This is another slide showing the exact same thing. You have a molecule where you make a planar carbocation. Nucleophile can come in the front or the back, and you end up with two possible products. I guess in this case, they're both the same because there's no chiral centers. But because it's flat, you can have attack on either side with equal probability. Yeah, just another small term here. Solvolysis just means the nucleophile is the solvent. So in this case, the nucleophile is water. So we call this solvolysis. Okay, so how do we know if something goes by SN1 or SN2? We can tell by the structure, methyl or primary is always SN2 because you can't form methyl or primary carbocations. Tertiary is always SN1 because you can't do SN2 because the backside is blocked. Secondary could be one or the other. Either one of these can happen, depending on the conditions. So what conditions for a secondary favor SN1 over SN2? So we're going to talk about that just for a minute. Things get really exciting next class too. We're going to throw a few more wrenches into things. This is, I find, the chapter where a lot of different factors all kind of come together at once. And if you can make it through this chapter, you're going to be set for the rest of the course. If you can stay with me for all of these different things we're going to be talking about. Okay, concentration and identity of nucleophiles. So think about an SN2. An SN2 has, as its rate determining step, nucleophile plus substrate. Siri, no, I don't need you. So if you have a nucleophile that's higher concentration, you're going to speed up SN2. Make sense? The rate for an SN2 equals K times concentration of nucleophile times concentration of substrate. You increase the concentration of the nucleophile, you increase the rate. You increase the concentration of the substrate, you increase the rate. This is for SN2. For SN1, rate is just K substrate. So increasing nucleophile doesn't help SN1, but increasing the concentration of the nucleophile does help SN2. So where we say secondary can be SN1 or SN2, let's say you want SN2. Why might you want SN2? Because you don't want to lose your stereochemistry. You're okay with inverting it, but you're not okay with throwing it away. If that's the case, you can ramp up. You can put as much nucleophiles you can possibly cram into solution there. That will speed up the SN2 and have no effect on the SN1. The other thing is it depends very strongly or very deeply, I don't know what the word I'm looking for is, on what the nucleophile actually is. Some nucleophiles are very strong and some are kind of not so strong. We go back to our analogy where your car is trying to push another car out. If you are driving a Ford F-150, you'll have an easy time pushing that car out and taking its place. If you're driving a bicycle, you won't, right? It's the same sort of thing when these nucleophiles come in. If you use weak nucleophiles, and weak nucleophiles are generally neutral. Strong nucleophiles tend to have negative charge. They are a little more hot to get at a positive carbon. Then you can speed up SN2 by using stronger nucleophiles. I want to just look at an example. I just want to slow down for a second. I want to show you this example, Br, and what we're going to do is use hydroxide. Hydroxide as a nucleophile can come in and it can make this. Great. Instead, we could have used water. Water would look like this. So one of the lone pairs on the oxygens has turned into a CO bond. And if you have another water molecule lying around, it can remove one of the hydrogens. And you can make the same product as you did in the first case. Both of these are SN2s, the way I've drawn them. So the second one required an extra step, but it's an acid-base step. Acid-base steps are almost always super fast. So this would be the slow step. This would be like super fast. So which of these two reactions, the top or the bottom, do you think is faster? The top one, and a lot of people will look at this and say the bottom one is slower because it's 2 steps. No. It is slower, but has nothing to do with the number of steps, especially if one of those steps is super fast, right? It's like, let's say we have 2 reactions. One is you're going to fly to Vancouver. The second one is you're going to fly to Vancouver and then open the door of your car and drive 10 minutes to your hotel. Or I shouldn't say that. You're going to drive to Vancouver, and once you hit the Vancouver airport, you're going to drive to your hotel. That's 2 steps, right? It's still going to be a lot slower. It's not slower because you had to drive an extra 10 minutes. It's because planes are faster. I don't know if that made any sense or if that confused things. I confuse myself sometimes. The reason this one is faster is because this is a much stronger nucleophile. Why is it much stronger? Because it's got a negative charge. It's got 3 lone pairs and a negative charge. It's much, much, much reactive than water, which is pretty happy all on its own. It's not very reactive, doesn't really have a big buildup of negative charge. It's fine being just water, but it will do this reaction if you make it. But a strong nucleophile will happen a lot faster. Okay. It's 9:19. I don't want to get into solvent effects just yet because I am not going to be able to do it justice in 1 minute, and we have the time is 9:19. So just a note for everybody, I am going to be starting my office hours in just a few minutes once I get myself downstairs back to my office. If you have any questions, please join on the team site, and I'll be happy to help anyone out till 11. Perfect. Goodbye, everybody.
Thank you.
See ya.